All right, you guys, we are officially on the last section for this course, 5.3, Inference for the Least Squares line. So there's going to be quite a bit of review in here from some of the stuff we did first semester, which will be good for anybody who forgot about that kind of stuff. But this is going to be our last section. Again, we're going to talk about confidence intervals and hypothesis tests. But this time, we are doing those intervals and tests for regression lines. So a little bit of review about regression lines. It's been a while. So remember with a regression line, basically we're taking a set of data, and if I were to plot that data, I would get a scatter plot, right? We call the blue dots over here a scatter plot. And if I want to make a prediction, so I have data here for very specific numbers of songs in relation to the minutes that are on those CDs. But if I wanted to predict maybe the number of minutes on a CD that has 14 songs, there's not any specific data here for that. So we would use this regression line here in green to predict other future values of Y, future number of minutes on a CD with a certain number of songs. So just quick review here. First of all, if I wanted to do things with this data, we know we can open up our calculator here, turn it on. You can click your stat button and then edit. And then you can put all that data into your list. And when we're working with this type of data, this bivariate data, remember we're calling it bivariate. There's two variables here, CD and songs. And I put all that data into these two lists. My list one is the number of songs on a CD, and my list two is the number of minutes on those CDs. So from here, I can create the scatter plot that they have here in blue by going to my stat plot option, hit second stat plot. And as you can see right now, all my stat plots are off. So I'm just going to choose the first one, turn it on. And this first type of plot I see here, it looks like scattered dots, that is a scatter plot. So going down from there, I choose my X list and Y list. And remember on this, your X variable should always be your explanatory variable. And your Y variable should always be what we call the response variable, remember that? So we are predicting here, or trying to determine if the number of songs on a CD explains the number of minutes on a CD. So you can see songs is going to be my explanatory variable and minutes is going to be my response variable. So back here, my number of songs is in list one, my number of minutes is in list two, so I'll just leave this exactly as it is. And then I can go ahead and hit my graph button. And of course, it usually goes to this standard screen right here. So I'm going to need to adjust my window. And the easiest way to adjust my window when I'm just looking for a stat plot is to go zoom and choose option 9, which is zoom stat. That gives us our stat plots nicely. So I'll click zoom 9 and it gives me this picture here, which looks just like that picture there. See? Okay, now the line here, as I said, the line is going to help us predict future values, future numbers of minutes on songs when we know, or future number of minutes on a CD when we know the number of songs. So to get this line, first thing we're going to do is we're going to calculate the line in its algebraic form, which is y hat equals a plus bx, where a, of course, is the y-intercept, and b is the slope of the line, which in statistics we actually call that the regression coefficient. So make sure you know that word. Talked about it before. And then x, of course, is just any x value. We use the x value to predict the y value. So generally, once we have this equation sorted out, we would plug in an x value and use it to calculate a y value. So let's go ahead and get this equation real quick for the data that we have above here. So to do that, the first thing you have to do is enter your data into the to list. We already did that. Enter data. into two lists. Okay, and then we've done this before to get that y hat equals a plus bx, that linear regression equation. We're going to hit the stat button, go over to calculate, and we're going to choose the option lin reg a plus bx. So let me do that. So I've already got my data in my list, so I'm going to go straight to my stat button, go over to calculate, and I'm going to go down until I say lin reg a plus bx, which mine is option 8 here. I'll hit enter. It asks you again, what's your x list, what's your y list? Just like I said before, my x list is 1, my response variable is an L2, and then frequency list, we're never really going to need to worry about that in this class. Like I've said before, you never need to do anything with that. But down here, store reg EQ, remember what that does? I can put a y var in here, and it will store the equation we're about to calculate in my y equals button, so I can graph it super easily without having to type all those numbers in. So to do that, to put that number, that y var right here, I'm going to click my vars button with that spot highlighted, go over to y vars, choose option 1, we're looking at a function, a linear function, and then I can really choose any of these. I'll just choose y1. We're just going to put it at y1 in my y equals screen. So there we go. Now you can see I have a y1 right there. So when I go down and hit calculate, it gives me my linear equation, y equals a plus bx, where a is 26.141888525, and b is 1.816420765. And as I said, it should have stored that for me here. There it is, that equation we just got is already right here, stored in my calculator. So I can, now that that's already in there, all I have to do is hit graph again, and it's going to put that line on my graph over top of the scatter plot that I already have in there. There it is. So now my picture looks exactly like their picture. And you can see the scatter plot, which is our actual observed values, and our line, which is our predicted values. And as you know, if I take any observed value and subtract the corresponding predicted value, we get what we call a residual, right? All of that stuff we're going to talk about again today. Another thing, let me go back here. Oh, it's not there anymore. Let me just real quick, mode. I think this computer calculator has my stat diagnostics off. This is stats class. Make sure your stat diagnostics are on. And let me do that again real quick. Stat calculate lin reg a plus bx. Calculate. There we go. I had some numbers missing down here. Remember R? Remember R? R was called our correlation coefficient, and it tells us how closely our observed values fit our regression line. So our R value here is 0.8. And remember, R is always between -1 and +1. The closer R is to either +1 or -1, the better a fit our line is for our scatter plot. So 0.8 is pretty decent. It could be better. We like to have like 90% and better, right? But it's nowhere near 0, so we're pretty safe here. I'm going to put that note in here because I feel like that's something we should definitely remember as well. So recall R is your correlation coefficient, not to be confused with the regression coefficient. Correlation coefficient, which shows the strength of the association and direction. Shows the strength and direction, right? Because if it's positive, it means it's increasing left to right. If our R is negative, that means it's decreasing left to right, yeah? So it shows the strength and direction of our association. And lastly, also remember, R is always between a -1 and a +1, where a perfect fit on a line is going to be exactly 1 or exactly -1, and no correlation at all would be 0. Okay, so all that is reviewed there. Some more things that we talked about a little later first semester was B can be calculated by taking that R, that correlation coefficient, and multiplying it by the quotient of the standard deviation of our Y value over the standard deviation of our X value. That was another way that we could find B, the regression coefficient or the slope of the line. And we also had that a line must always go through X bar comma Y bar, the mean of the X values and the mean of the Y values here. So if I use this point here that is guaranteed to be in our line and plug it into our regression line equation, we can also calculate our A, our y-intercept if we need to, by taking our Y bar minus B times X bar, plugging in that guaranteed Y bar X bar combo. All right. And then the last thing, I guess, too, Y hat. Remember, we call it Y hat, not Y. Y hat means we're looking at predicted values, not actual guaranteed values, which is going to make sense also because later on in the section, we're going to talk about how we can use this to get estimates. Okay, a predicted value is an estimate. All right, down here, we have some computer data for this set of data that we have up here. So we can't actually compute this data because we don't have this program, but you will have to interpret this kind of data on your tests and on your exam. So on this, so this is, again, this was generated from this data up here. So you can see right away, remember on our calculator here, we had our regression line was a plus bx, where a is this number and b is this number. You can see the same thing here. Here's a, and here is b. So I can see this, the y-intercept of my regression equation is 26.14, and the slope of our regression equation is about 1.8. Okay, so that's super helpful also. So if I was given this data here, they might just say like, what is the regression line? And this is all I give you. Well, by looking at this, we see right here, A, where the constant of the coefficient, that's our y-intercept, and B, the coefficient of the number of songs is 1.8. So we can say y hat equals 26.1419 plus 1.81642x. Or in context, we would say the predicted number of minutes on a CD is equal to 26.1419 plus 1.81642 times the number of songs on that CD. Okay, so we could figure that out just using this data, this data output here, and you will definitely have to do that. Some other things here that we'll talk about later on. You can see the degrees of freedom is given to you, which we know we need to use degrees of freedom to do intervals and hypothesis tests. And we also have S here. We'll talk about S in a little bit. We're going to be using that as well, though. Yeah, and we'll come back to that. There's also this number here is going to be important, and this number here is going to be important for our hypothesis test. This is actually our test statistic and our p-value for a 95% confidence interval, a two-sided 95% confidence interval. Pretty cool. T and P. All right, over here we have a residual plot. We talked about these before too. A residual plot is what we use to determine if a line is even a good fit at all for this data. Meaning sometimes we have scatter plots that are best modeled with like a parabola, like a U shape, or maybe they're best modeled using an exponential function. So in order for us to make sure that a line is the best choice, we look at this residual plot. And so when we look at this residual plot, what we're looking for is randomness. So if a line is a good model for the data, then the residual plot will be randomly scattered. Randomly scattered above and below that horizontal line you see there. You don't want it all above or all below. It needs to be kind of even and evenly scattered. Okay, so we can see here in this one, it appears to be pretty random. Usually if a line is not a good fit, then you'll see a really obvious like curve in here. And so it would be pretty easy to see like, whoa, there's a very specific U shape in here. A line is not a good fit. We need to do something else or we can't do anything at all. So let me just go over before I even write that down. Let's talk about how I can make this residual plot here. So to make a residual plot on your calculator, remember I already have the data in my two lists here, and I've already calculated that, that regression line in my calculator. So those are the first two steps. If you want to do a residual plot, if you want to calculate residuals at all, you have to put both your lists in here. And second, you have to calculate your regression line, that y hat equals a plus bx. After those two things are done, I'm now going to go over to my third list here, which is currently empty, and highlight the L3 and hit enter. Okay, we've done this before, so this should sound familiar. So now I'm going to tell my calculator that I want list 3 to be my residual values. And remember, residual is all of these observed values here in list 2, minus the predicted values generated from the line we calculated. So to do that, it's very simple. We're just going to hit that stat button again. Actually, we're going to go to list. So you hit second stat to go to list. And this is what you see. And you might need to scroll down further than me, but you're going to choose the option RESID, which is short for residuals. And I'll hit enter there. And it says L3 equals the list for the residuals. And when I hit enter now, it's automatically going to calculate those for me now using my response variable and the line that was previously calculated. So if you don't calculate your line first, it's going to give you an error here. So I'll hit enter. And bam, there are all of my residual values for my entire data set. Pretty cool, huh? So now that I have a list of my residuals, I can very easily create this plot here. And they use the predicted values on their x-axis, but they do also say on Apex that we can also use our observed values here, and you'll get a very similar set. So we can use a response. Usually we do residuals and response. So that would be L2 is my response. L3 is my residuals. So to do this, I'm just going to create a scatter plot. It's just a scatter plot where my x value is actually my response, L2, and my y values are going to be my residuals, which are in L3. So again, to do that, I go second, y equals to get to my stat plot, and I'll just use the same one I had before. In fact, I'm going to go here real quick and get rid of this because it's going to be in my way in a second. So now I'll go second stat plot. Okay, I still want a scatter plot, but now my x-axis is going to be my response variables, L2. So I'll hit second 2 to get an L2 in there. And my y list is going to be my residuals, which I just put in L3, second 3. So now I'm going to hit graph, and I'll probably need to adjust my zoom again because I had it in a different spot just before. So I'll go zoom 9 once again to get my zoom stat option, and this is what I see. And as you can see, I used my observed values. They use the predicted values, but either way, all we're looking for is randomness and that we have about the same number of points above and below the line. And we definitely have that in both cases. So yes, based on this, we can say a line is a good model for this data. A line is a good model for this data because the residual plot shows no pattern. It's completely random above and below the line. Okay. All right. So moving on. Okay, so let's move on to something new now. So all of that was actually, for the most part, it was review. So now moving on, we're going to use this regression line now as a model, as a point estimate for a population. So traditionally, we use Greek letters to represent population parameters, like mu and sigma and all of those ones that we've been looking at. So now the Greek, we're gonna write this as with Greek letters so that it looks like this. And actually there's a little bit of a typo in here. It should really say, instead of y hat, it should say, I can't scroll over, it should say mu sub y. Okay, and they've explained why that is in the Apex tutorial, but basically because the true regression line for the entire population that we are trying to make predictions on is going to have the slope and y-intercept for the average y value at any given x value. Meaning at any x value, like say x is 10 CDs, there's obviously going to be more than just one CD that has 10 songs on it. So for 10 songs, we're going to look at the average number of minutes on that CD. Okay, so that's the way that that is written for our parameter, our population parameter, and that's what we are trying to estimate here. So just like before, B naught is going to represent our y-intercept, and B sub 1 is going to equal our slope for the linear regression equation of our population, our whole population. And so we're going to estimate that with a sample, of course, like we always do. So when we do our sample, y hat, our predicted y value, we're going to use lowercase b sub naught to estimate the beta sub naught. And we're going to use a lowercase b sub 1 to estimate beta sub 1. So you can see there's really not much change between what we have here and what we have up here and what we have over here. We're just using different symbols. Okay. And then of course here, SRS, as always, we always want simple random samples. So the two conditions that have to be met in order for us to make predictions based on this is that the residuals need to be normally distributed about the regression line, and the standard deviation of the residuals needs to be about the same for each value of x. So to do that, to tell if the residuals are normally distributed about the regression line, we're going to look at a normal quantile plot for the residuals. And of course, you'll see some examples. I'll do that. And in order to determine if the standard deviation of the residuals is the same for each value of x, that's again where we're going to look at that, that residual plot. Look for randomness, no pattern, in the residual plot. Okay. All right, and then down below here, we have some more equations as we've seen before. I gave you these first two on that first page. We just talked about this here. And then it gives us here this estimate of sigma that we're going to use. Remember how in our confidence intervals and in our hypothesis tests, we end up using S to calculate our margin of error. This is how we calculate that margin of error by hand. But no surprise this far in, we're pretty much going to be using our calculator or some given data output, some computerized output to get these numbers for the most part. So I will go over how we can do all of that in each example. We've got 2 more pages. All right, so first let's start with confidence intervals. So here it says we have a table that shows the average round trip coach airfare paid by customers of American Airlines on each of 18 heavily traveled U.S. air routes in 1996. The numbers come from Consumer Reports magazine in July of 1997. So yeah, it has a little out of date, I know. Can we predict the cost by knowing the distance of flight? We can use linear regression to find out. Okay, so we have, again, some computer data here. They've given us all of these plots and stuff, but I also kind of want to show you how to do it on your own, mainly with your calculator as we go through this. So the first thing I'm going to do, I'm going to pretend like they didn't give us any of that data output or these scatter plots over here, and that maybe all we have is this data, okay? And we'll go through how we can get all the stuff that they have using your calculator as well. So the first thing I'm going to do is I need to put this data into my list. I'm going to put distance in list 1 and cost in list 2. So I'll pause to do that. All right, so you can see I've got all that data in my calculator here, and we're actually going to use this exact same data, this exact same table in the next example as well. So if you want to pause this video and put that in your own calculator just so you can follow along, that'd probably be a good idea. So the first thing here that we're going to do, of course, is we're going to look at the scatter plot and just kind of get a general idea for what is going on. So to get the scatter plot, just like they have here, again, we go stat plots, choose the scatter plot option, and our data is in list 1 and list 2. And I'll hit graph. Probably need to adjust my zoom. Best way to do that is zoom 9. And there we go. It looks just like what they have on the paper. I see a little bit of kind of fanning out here, which is a little concerning about my standard deviation condition, but we'll look at that again later on. It does appear to be positively associated, right? It's continuously increasing, and I can kind of with my mouse draw where I think the line of regression will be through the middle of this data set. So I can go ahead now and calculate that line. Again, to calculate the line of regression, the y hat equals a plus bx. We go to hit the stat button, go over to calculate, and choose the option that says lin reg a plus bx minus option 8. Our data is in list 1 and list 2. And take advantage of this store reg eq here because I would like to see my line transposed over this data anyways. In order to put that in there, we go hit bars, go to y bars, choose function, and I'll put my line on y1. Now I'll calculate, and again, you don't have to put that there if you don't need that line, but most of the time it's going to be really handy to see that. So I'll hit enter, and there we go. There's my line. Y equals a plus bx, where a is 128.6-ish, and b is about like 1.13-ish. And we can see here our correlation coefficient R is about 0.836. So it's a pretty high number, so it looks pretty good so far that this is going to be a good model. We do still need to check our residual plot to make sure there's no pattern in there though. So I can say just from what we just had, on our calculator, y hat was a 128.577 plus b 0.127153x. Now, cool thing here, they actually give you this data output as well. So remember, again, on this, here's A, here's B. We get the exact same answer we had using our calculator without any work at all. All right, so now that I've got my point estimate, I'm going to go ahead and check my conditions. So the first condition, or actually I guess this is probably the second condition I had listed before, was we needed to check the residual plot. This is a residual plot. To make sure that there is no obvious pattern here. We want to see random scattered. So there is no major pattern, no pattern, randomly scattered. So that tells us that a line is a good estimate or a good model. the line is a good model for the data. Okay, doesn't tell us how well it fits it, just tells us like it's not like going to be quadratic or exponential. A line essentially is a good model. And then the next condition we have to check, we have to make sure that the residuals are normally distributed. And anytime that we need to check for normal distribution, the good way to do that is to look at a normal quantile plot. Normal quantile plot. In a normal quantile plot, if the points follow a perfectly straight line, then that means we have a perfectly normal distribution. So you can see that these points are almost perfectly straight. And this is a normal quantile plot for the residuals, because we need to determine here if the residuals are normally distributed. I can do a normal quantile plot for any set of data though. So again, these residuals appear to be very close to a line. They're not perfect, so it's not perfectly normally distributed, but it's very close to being normally distributed. So we got close to a line. So the residuals are approximately, not perfect, obviously, approximately normally distributed. So those are our two conditions. Okay, so let's talk about how we can do, what if they didn't give us those plots? How would I get those plots in my calculator? So I showed you this one a little bit ago to getting the residual plot. So, and again, I'm not going to use the predicted. Usually we use the response variable here, not the predicted. So I'll go here. And I need to go back to my lists, first of all. Well, actually, I need to make sure I have this in my calculator first. If you haven't calculated the actual line using your calculator, it'll either give you the wrong residuals or it won't give you residuals at all. So make sure you've done this. Even if they've given you this, you have to do this to be able to get residuals, okay? So once that's done, I go back to my lists, go up and highlight an empty list, hit enter. So my cursor is down here. And now I'm gonna put in here residuals. So I'll go to my list option, second step, down. You might have to scroll down a lot farther than me to option 7, residuals. So I can see L3 equals the list of residuals, hit enter, and they're automatically calculated for you. So now that I have my residuals in here, I can make my residual plot. Go up to your stat plots. A residual plot is a type of scatter plot, so I don't need to change that. But now my X list needs to be my response variables, L2, and my Y list needs to be my residuals, which are in L3. Oops, oh goodness, L3, there we go. And we go graph, got some weird thing going on here. Oh, the line is this line, so I can clear that out. And also my zoom was all kinds of off, so I'll hit zoom 9 to recenter that. And again, mine isn't exactly like theirs, it's very similar because I used my response variables here, whereas they use the predicted. Either way, we're only looking for scatter above and below. And again, there's a little bit of like kind of like a swooping thing going on here, but not too much of an obvious pattern, so it's okay. So that's my residual plot. And then moving on to my normal quantile plot, I'll go back to my stat plots here again. So to do a normal quantile plot, that's this last option here that looks kind of like a line. It's actually not a line. That one there. Okay, and you can see here, it's only asking for the data list. So what are we wanting to check the normalcy of? We're wanting to check to see if the residuals are normal. So I'm going to change this L2 to the list where my residuals are, L3. And my data right now, it has it in list X, and they talk about an apex. Now it doesn't matter if I put my residuals and my n scores on the opposite axes. On this one here, you can see they have the residuals on the y-axis. So if I want it to look just like this, I'll go over and highlight y. And again, it's not going to matter either way. If I swap my x and y, it's just going to change the direction of this line, but it still should appear linear either way. So I'll hit graph. I need to adjust my zoom again, zoom 9, and there it is, the exact same plot that they have here. Okay. All right, so now that we checked all our conditions and we went over lots of review on how to get those different plots and whatnot, let's actually do our confidence interval. So calculating the confidence interval itself is very simple. We're just going to use this formula here, which is our, as always, our point estimate plus and minus our margin of error, where our margin of error is our critical value, happens to be a t star here this time, and times our standard error. All right, so let's, what we already have, B sub 1, we calculated above, that was our 0.127153 from our line. All right, T star, let's see, T star I can get from my table. So remember, in our T table, we need to know which size of the interval we're going to do, which is a 95% interval. And we also need to know our degrees of freedom. So the degrees of freedom, as we said before, is always going to be n minus 2. So the number of our sample size, or the size of our sample, minus 2. And the size of this sample, if you go back up and look, is 18. So 18 minus 2 is 16. So let's real quick go to our T table, maybe. T table, there it is. And look for 95% at the bottom and a T value, or sorry, DF of 16. So DF of 16, confidence interval is 95. So we're up here at 2.12 for our critical T value, 2.12. Okay, and then lastly, we need SE sub B1. And they let you know in Apex that you will not have to calculate SE sub B sub 1 by hand ever. They do give you the formula, so you can look at that there though. But if you look up here, here was B. Here's the SE of B. SE of B sub 1 is 0.0209. 0.0209. So that's all that we need to be able to calculate our confidence interval. So let's go ahead and do that. Oh, another thing also on that data entry up here, you can also see your degrees of freedom up here. 16 degrees of freedom. Yep, it's all given to you. Back down. All right, so let's go ahead and calculate this. We're going to do B1 plus or minus T star times SE, the standard error of B sub 1. So plugging things in, B sub 1 was 0.127 plus or minus T star was 2.12, and the standard error we just found was 0.0209. So when I subtract, I get my lower bound of my confidence interval, 0.083, and when I add, I get the upper bound of my confidence interval. So there it is. We are 95% confident that the true slope of the true population regression equation is between these two numbers. Which brings us to the last example, hypothesis tests. So doing a hypothesis test for the slope of a regression equation, we are always going to have a null hypothesis where we assume that our population slope is going to be equal to 0. Okay, why would I say that? Let's go straight to that actually here. When I say that my null hypothesis is that the slope of my regression equation is 0, remember this, when the slope of a line is 0, that means it's a perfectly horizontal line. And if my x and y my x and y variables had no association whatsoever, then they would be kind of randomly scattered with no real association obvious at all, right? We've seen that before. So imagine if you have data like this and you try to create a regression equation for it, it's going to give you a horizontal line. So when your regression equation has a slope of 0, or when your regression equation is horizontal, a horizontal line, that pretty much tells you that your y variable and your x variable are not associated, which means we cannot use the x variables to predict the y values, okay? And that's what we're trying to determine here. Can we use the x values to predict the y values? Are the x and y values associated? So when we say that the slope is 0, we are really saying that the x values, the distance of a plane trip in this case, cannot be used to predict the y values, which in this case is the cost of a flight. Okay, so that's what that means. And since I'm here, usually we go check our conditions first, but since I'm here, I'll go ahead and put my alternative hypothesis as well. In this case, my alternative hypothesis can be either one-sided or two-sided. So it can be that B1 is greater than 0, B1 is less than 0, those are both one-sided, or it can be two-sided, and I can say B sub 1 is not equal to 0. Okay, and that's what we're trying to determine here. We're not trying, if we were to try and determine if there was a positive association, that would mean the slope would be a positive number. If we were trying to say there was a negative association, then that would mean the slope is a negative number. In this case, we're just trying to say there is an association. So we say that there's just anything but 0. Okay? So slope is not 0, which means distance can be used to predict cost. Okay, in fact, I'm going to come up here real quick, and I hopefully have more room than me, and just add that in here. Your H sub A can be like this, where there is a negative association, which means that my scatter plot is going to be decreasing left to right. We can say that it is a positive number, or if our slope is positive, that means that it is positively associated. Which means our scatter plot is generally increasing left to right. And then, of course, we have what we have down here is just that there is an association in general. Okay. So before I actually do the test here, which there's lots of ways to do it, we need to go back up and check our conditions. Luckily, this is the exact same set of data from the last example, so we already did this. So were the residuals normally distributed about the regression line? Yes, we looked at the normal quantile plot for that. The normal quantile plot from last example. And are the standard deviations of the residuals roughly the same for each value of x? Again, yes. See the residual plot from the last example. Okay, so we already checked both of those conditions. We confirmed that they were A-OK. So we can move on now to step 3. As always, state the test we're going to use and the significance level. So since we don't know the true standard deviation for the slope of the regression line, we are going to use a t-test, just like how we did a t-confidence interval. We will perform a t-test for the slope of the regression line. which is not the same button in your calculator in case you're wondering, but I will go over that, with, gotta say your significance level. And we were told to do this at a significance level of 0.05, as always, right? Okay, so moving on. Let's go ahead and calculate our test statistic. So here is the formula for calculating your test statistic by hand. So let's do that first, and then I'll show you all the shortcuts. So by hand, not a big deal. We already know these numbers. B sub 1 was 0.127153. See the last page. It's also right here. And SE sub B1 was 0.0209. It's the standard error. And again, you can see that in the last example, as well as doop, 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 right here. So when I divide those two, I get my test statistic. And I'm actually going to write it down here. T is 6.08. So there's our test statistic, 6.08. So then we should be able to use our t-table or our calculator to calculate that p-value. So right, our p-value this time is the probability that t is not equal to 6.08. So I would look above as well as below the negative version of 6.08 and combine those two together. Or I would just look simply above and then multiply it by 2. Right? In fact, let's go ahead and do that. So what's the probability that t is above 6.08? Remembering our degrees of freedom was 16, right? Degrees of freedom, n minus 2. There's 18 data pieces here. Minus 2 is 16. So 16 and 6.08. Got a lot of things going on here. Let me erase a bunch of it. So here's my 16. Okay, and we're looking for 6.08. If you look at this list of degrees of freedom 16, it never gets that far. The highest I get to is 4.015. So we know we're definitely further this way, which means our tail probability is going to be definitely less than this number, which we're going to have to double because this is a two-sided test. But even if I were to double this number, I still wouldn't be greater than my alpha, 0.05. So this is looking like we can reject our null. Okay, but since we have lots of other resources, let's see if we can get this exact p-value. Okay, so first thing I would do, maybe on my calculator, we got lots of options now. I'm going to show you all of them. So far, what you already know how to do, I can hit the stat button, go over to tests, and we can do, or not tests, calculate, where am I? Distributions menu, that's what I want. My distributions menu, and I can go to that TCDF we've used a lot. And I can look simply just above that 6.08, 6.08 to a really big number with degrees of freedom 16. And we get this teeny tiny number, right? 0.0000796. All right, and then we would multiply that by 2 since this is a two-sided test and that's only one tail. We need 2 tails. And that gives us our actual p-value is 0.0000159. Cool. Okay. There are simpler ways to do this though. Let me go back to the notes that we were already looking at. You should notice something about this data set here. T was 6.08. Hey, look, there's T. Our p-value was 0.00001. There's our p-value. So when you're given this set of data like this, you're given pretty much all the information you could ever ask for. So we had our entire linear regression equation with these two numbers here. We had the standard error of our slope as well as actually your y-intercept if we needed it. We have the test statistic as well as the p-value and the degrees of freedom, 16 here. We have all kinds of stuff. So I didn't even need to calculate anything. All of my information is right here. One other way we can do this, go to your calculator again. Remember, I already have all this data in my calculator, okay? That's important. I don't necessarily need this one anymore. The residuals is really just to check your conditions. In fact, just to prove that, I'm gonna get rid of it. So I'm gonna now go to my stat button and move over to calculate, or not calculate, tests. Remember our test menu where we can do all of our hypothesis tests and our confidence intervals? Well, for this section, the buttons we want are all the way at the bottom. Lin-reg t-test, lin-reg t-interval. Yep. So if I go up and highlight lin-reg t-test, tell it where my data is, list 1 and list 2. Yes, you have to have the actual data in here. Choose the type of test we're doing, two-sided, less than or greater than. We did two-sided. And calculate. And it tells me right here, my t value is 6.08, 6.09, I guess if we round. And our p value is 0.0001, exactly what we had here as well. Okay, it even tells us in here our degrees of freedom, and our a, our y-intercept of our regression equation, our b, the slope of our regression equation, and all kinds of other stuff in here, all in one screen. How awesome is this? Okay, now if I remember the last example, we did an interval for this same data. Go back to that stat button, go over to tests, all the way to the bottom. Lin-reg t interval, mine's option G. Again, where's your data? List 1 and list 2. What kind of level did we do in that last example? A 95% level. Calculate. Bam, there's the interval we had in the last example, exactly what we got using just the calculator. And again, it also gives us a bunch of other information too. Here's B, here's our degrees of freedom, here is A, R, all of that stuff right there with just a few clicks. But you do have to have your data in your list first to do that, okay? All right, so no matter how you got it, the probability 0.00001 is super small, definitely less than alpha, so we reject our null. Since our p-value is less than alpha, we reject H naught. What does that mean in context? Look back up at your hypotheses. That means we can support our alternative. The distance can be used to predict the cost. Come on, it's not scrolling, hold on. The distance of an American Airlines flight can be used to predict the cost because they're associated. All right, awesome. Okay, so the last thing we have on here is just a word of caution. When we're using our calculator, we get to choose what type of test that we're doing. But as you notice, that's not really an option here. This p-value that we have here, the 0.00001, is only for a two-sided test. Remember, a two-sided test, the p-value is twice as big as it would be on a one-sided test. So if you were given this data output here and you need to do a one-sided test instead, we would just need to make sure that we take that p-value that's there and divide it in half. No big deal, as long as you don't forget. All right, and that is it. There's a bunch of pages after this that go over all the stuff that I did with my calculator kind of in detail. So if you need to, you can look over that. You can ask me for help. But other than that, we're done. And after this, it's just review, and eventually an exam. So let me know if you need me.